Okay, so hi everyone. Today we'll be going through feed-forward neural network. So it means that it marks the start of our departure from those conventional ML algorithms into deep learning, which is the most relevant to the kind of AI structures that you'll be using for competitions. So once again, because all of you are already in your TL teams, we encourage you all to quickly go and get your consent form sorted out and submit it before you forget. Yeah, because you should get that out of the way as much as possible. So before Yiqin starts the lecture on feed-forward neural network, I want to consolidate the three things that we've learned so far. So if I want to bring your attention to the ML chat, right? I'll bump the message once again. I sent this a while back. And basically, the message says that there are four most fundamental concepts in order to understand like machine learning, which are namely loss and gradient descent. That's number one. Number two is perceptron. Number three is non-linearity. Number four is high dimensionality. So when we first started out with the linear regression project, we learned what is the concept of empirical risk and loss, right? As loss as a measure of how far away our predictions are from the correct answer. Then gradient descent is therefore like a method that uses differentiation to minimize the loss, to find the combination of parameters that minimizes this loss. So you will see later in the feed-forward neural network that the same concept is being applied. It's just that because the feed-forward neural network, the name network suggests that there are multiple individual units in the structure of the network. So essentially, the gradient descent is still being applied across the entire network, but because there are multiple units inside the network, you must apply the gradient descent over each unit as well. So later you will see that there's actually an application of chain rule in order to minimize the loss for an entire neural network. Then after we learned the linear regression, and we did a linear regression project, we went on to perceptron, right? Where we learned linear classifier, where based on the naive way, which was based on the angle, when you dot it and you add the bias, then you can tell whether it's on one side of the plane or the other, and that will give you the class, right? So this perceptron, like the act of dotting the input against weight and then adding a bias, this is basically the fundamental unit of the neural network, and it basically consists of one neuron. So later you'll also see that the neural network is basically interconnected like a graph of these individual perceptrons. Then I'll just jump to point 4, which is high dimensionality. So after we learn our linear classifier, we went on, Yiqin went on to teach the kernel trick, right? Which was basically to explode a given data set into infinite dimensions such that you could draw a hyperplane that splits them. And this is very important because it means that if you want to model relationships or you want to classify complex data sets that cannot be easily separated in the dimensions that we are used to, like 2D, 3D, that will mean that you will need to make use of high dimensional data. So in the future, when we talk a lot more about deep learning, you'll hear terms like latent space, high dimensional classification space being thrown around. These essentially all refer to the same idea of trying to represent the data set, the input data, in a high dimensional form, where input data of similar features are grouped closer together in the high dimensional space, such that you could draw decision boundaries that effectively separate them. So with those three concepts done, the only one remaining will be non-linearity. So that is the subject of today's lecture, which aims to introduce the idea of non-linearity, the idea of activation function, why you need to apply things like sigmoid or the logistic family of functions in order for you to approximate complex relationships. And later on, Yiqin will also talk about something called universal approximation theorem, which states that if you chain enough nonlinear functions together, you can basically approximate anything. Yeah. So that's basically like a preface to what we're gonna go through today. And the feed-forward neural network would be the basis of the other complex structures in computer vision, like convolutional neural network, and in NLP, like recurrent neural network. Yeah. Okay, so it's over to you.
Hello? Oh, okay, you all can hear, right?
Yeah, I can.
Okay, shut the fuck up, then I'll ask you.
Oh,
Okay, let me share my screen. Okay, can see the notes.
can.
The recording is started, right?
Yup.
Okay, so today we're gonna talk about feed-forward neural network and yeah, linear activation functions and how we can do backpropagation for this kind of larger networks with more units. So we want to start off with the very basics of neural network, which is the basic unit that is the neuron, right? So let's talk about the basic structure of a neuron. So for a neuron in a neural network, essentially it's going to take some inputs. Let's say our input is x, and it's, let's say in this case we're dealing with a three-dimensional input. So we can actually split this x into x1, x2, x3, right? So we can have x1, x2, x3, and let's say we have these lines connecting these inputs into a neuron. Uh, and each of these lines actually represents sort of a weightage of these individual inputs into the neuron. So for example, this line can be W1, which is this is the weight, this is W2, this is W3, right? And what this neuron do is that it sums up all these weights multiplied by the input, and it adds a certain bias, right? So the bias term can be something like W naught. And then from this neuron, it goes, the output of this neuron, which usually is denoted as Z, it will go into another function. In this case, this function is actually called the activation function, which is usually nonlinear. And this is essentially, after this activation, it will produce the desirable output, which is like prediction, right? And we can actually express this entire sort of mechanism in just mathematically. So, so for activation function f, you're essentially operating this function on the summation of all the weights multiplied by the inputs. So in this case, we have three inputs. So it goes from x1 to x3, and it multiplies each individual weight, and then it all of them add to the bias, right? And that's your prediction. And if you have studied biology, this actually pretty much resembles a biological neuron, where you have this is your the body of that neuron. So that's your nucleus and whatever. So these are like dendrites, and essentially you can envision them as sort of inputs to your neuron. And these inputs can come from multiple different sources, like how we have visualized here. It can come from multiple different sources, and the length of these neurons actually represents sort of the weight of each of these connections, the strength, how much your input contributes to the overall computation. And then it's followed by an axon, uh, which has the endings, axon endings, that connects to other neurons. Okay, so this is very much biologically inspired. And you realize that you actually have already worked with such an architecture before, such a neuron before. In fact, your linear classifier is actually just a single neuron, right? So we can actually visualize a classifier, your linear classifier, as one neuron. So we have, in general, for a linear classifier, the x can be of any dimension. And this is, again, the formula for your linear classifier. So in this case, we're going to use w instead of theta and w naught. And for the perceptron one, you're taking the sign of your x dot w plus the w naught, right? And we can do it in the neuron form, which is you have x1, you have x2, it goes all the way to xd. And these are all connected to neuron with some weights, right? So your w1, w2, wd. And this one sums it up with a bias term. And it puts to the activation function, which in this case is actually just your sign. And that is your output of the classifier. So this is the exact same as this equation here, right? So then it can be said that a single neuron is essentially something that can give you a linear regression or linear classification. So it's very limited in terms of its capabilities. And from here, we can actually relate stacking of neurons to the idea of feature representation. So let's talk about the concept of hidden layers, which can be used to sort of expand the feature representation. Remember, we talked about feature representation in the last lecture, where we can sort of take your x of dimensionality d and we put it through a feature transformation function phi to obtain much higher dimension representation of it. So your x like this, and you put it into feature transformation function that will give you x1, x2, or something like x1, x2, so on and so forth. And this resulting thing is actually going to be a specific dimension that's larger than the original dimension. So you project it on higher dimensionality, which allows you to perform nonlinear regression, nonlinear classification. So for that case, our classifier was written like this. We're still taking a sign. So instead of operating on just x, we're operating on phi x. So one problem with this method, this approach, is that your phi is sort of user defined, and it's like you're using the same phi for all these different tasks. So same transformation for different tasks. Right. Remember the talk about kernel function where we say that in general you can just use the radial basis kernel. But for different tasks, you might want sort of a different method to transform your features, to project your features, to better suit it to that task, such that your model can perform better. So the idea of having hidden layers is that we will allow the model to learn these sort of feature representations by itself. So instead of us having to specify a function to project the original input into a higher dimension space, we can simply specify sort of how high dimension we want that representation to be, and then the model itself is going to figure out how it's going to project that representation. So we do not transform it beforehand. We simply take it raw and just put it into the model x2 and so on to xd. And I'm just going to draw these lines because I'm not going to connect every single one. So you can have many neurons in this hidden layer here. You have d neurons actually. In this case, because we specify a feature transformation of BD, so let's just have high dimensionality d. And from here, these can then go into your linear classifier, right? The single neuron at the end that goes through an activation and produce your prediction. So, and all of these neurons will have its individual activation as well. So essentially, this entire layer of neurons here is just for feature representation purposes. And because you can sort of define how large you want this layer to be, you can scale up the representational power of your model very easily by using more neurons. So we have been using this activation function here, which I said was nonlinear. So let's just have a little bit more understanding of what this nonlinearity is about, right? So nonlinearities.
Oh, wait, sorry. Why
Yep.
do you need multiple? Why do you need multiple neurons in a layer? Because isn't a single neuron already like weighing up everything?
You mean okay? So you're asking why we need a hidden layer?
Why do you need multiple neurons?
In this case, this
Yeah.
right? You're talking about this, right? So recall the feature projection function essentially takes your input, which is of a smaller dimension, small d, and you want to project it through some operation such that you have a higher dimensionality, a big D, right? So in this case, we are instead of trying to specify this feature projection function ourselves, we instead want the model to sort of pick out what it wants to do to the original inputs to project it onto a higher dimensionality. So to do that, you actually need this hidden layer, which will eventually produce you, because each of these will produce one output. So essentially, is trying to project this from a dimensionality small d to dimensionality big D.
So every neuron, it gives you a different linear combination of the inputs,
Yes, yes.
and those are the different features.
Yeah, so you can see that each neuron is going to sum up every single connection with the original inputs, right? And the output from that neuron essentially is the projected, when you combine all these, is essentially the projected features onto a high dimensionality. Yeah. Okay. So I think that's pretty straightforward because you guys already learned about feature projection in the last lesson, right? So let's just talk about a bit about these non-linearities, these activation functions. So there's actually many different types of non-linearities. So I've already introduced you guys to sigmoid in our first lesson. There's also other stuff like tan-h, which is essentially actually a class of sigmoid function. And there's also ReLU, and sometimes you can actually activate using linear activation, though that's not non-linearity. There's many more, and usually when you're working with different types of neural network, you probably want to use different types of nonlinearities. So let's take a look at some these three, for example. So your sigmoid is, you guys should be familiar with shape. It's that S-shaped function which goes from essentially squashes your value between 1 and 0. This 0, and the intercept's half. So this is your sigmoid function, and it's given by the formula. So in this case, let's say fx is equal to 1 plus e to the power negative x, right? So we already went through this, and the hyperbolic tangent function is also the same shape, just that it has a different value range. So it goes from -1. Okay, that's not very nice. It goes from -1 to 1. So just a different class of sigmoid function. So your tan-h function is essentially just the tan-h of x, right? And then ReLU is a little bit different. So instead of being smooth and continuous, it's actually like a two-stage function where this flat here, uh, it just takes a value of 0 if your input x is negative, and the rest is linear, right? So that's ReLU. So if you can, if you want to express it mathematically, is given by this. You'll take the maximum between 0 and the value of x. Right. So these are some more classic and commonly used nonlinear activation functions that's usually used to train neural networks. So recall that we use a nonlinear activation function for every single one of neurons. And actually, the reason why we do that is that this nonlinearity actually allows you to approximate very complex functions. So nonlinearity allows for the approximation of complex functions. And in fact, if you do not use nonlinearity and you have like a chain of neurons, the output of one neuron goes to another, and so on. You'll realize that if there's no non-linear activation function, so essentially you're doing linear activation for each of your neurons, your entire neural network is collapsible down to just a linear function. So it's just collapsible back to mx plus c. No matter how many neurons you put into your network, if you do not use non-linear activation function, and you can actually go try to work it out yourself. So everything can be collapsed back down to just this simple formula if you do not use non-linear activation function. And nonlinear activation functions has the essential aspect to allow your model to approximate complex functions. And one very intuitive way of thinking about it is that if you have a really complicated function that you want to approximate, see something like random like this. Step functions, so these little tower blocks that can be placed next to each other such that they eventually approximate the function, right? So the actual proof and mathematics behind this is quite involved. So I will actually drop you guys a link if you guys are more interested. So because actually in a 2D version, it's much simpler. So if you have sort of two neurons and you sum up their output, see each of the output can be, if we activate something like 10H, so each of the output can look something like this, right? Because you have a bias term which can shift your activated function. And if you really increase the gradient of that activated value, you essentially get something that's like straight, just like a step function. And this neuron can be a slightly different step function that's maybe slightly shifted and slightly higher. And if you have different weights, say -1 and 1, you're essentially creating that tower block that we're talking about, right? From these two functions. And by adding more and more of these neurons in a single hidden layer, you're essentially creating more and more of these tower blocks, which can be used to approximate a really complex function. And the number of neurons that you use actually determines how closely your neural network is going to approximate this function. So then from here, maybe we can bring a little bit of universal approximation theorem. But of course, the proof is also pretty complicated. So we won't be dwelling into the mathematics of this specific theorem. If you're interested, you can go read the papers. So there's actually two definitions for this. One is that you can approximate any function with a single hidden layer of arbitrary size. Right? And if you think about this, if you go back to this analogy to the feature transformation function that we talked about just now, if you can set any number of neurons for a hidden layer, you essentially have complete control over the representational power of your neural network. So you can set it to be very large, which gives you a very high representational power, thus allow you to approximate more and more higher order functions, right? So that is pretty intuitive to think about. And the other way is that you can approximate any function with a neural network of arbitrary depth. Arbitrary depth and a bounded width. So essentially, you're sacrificing width for depth. And this is actually the way that people generally do it. And actually, yeah, let's talk about why this is the case, right? So depth versus width. So why people choose to make the neural networks deeper instead of wider, because after all, both methods would allow you to approximate any function after all, right? So there are actually many different reasons. There's no definitive answer to why this is the case. and a lot of people would like to use empirical facts to show you that depth works better than width. But there are two pretty strong reasons why depth is better than width. The first of which is pretty practical. It's with regards to efficiency for computation and stuff like that. So let's say we have a sort of input that's two-dimensional, and we have let's say we want a hidden layer to have 10 neurons, right? 10 neurons. We can try to draw this. So we have two inputs, x1, x2. It has a row of 10 neurons, which are all densely connected with every single one of your input. So every single one of your input is connected to every single one of the neurons that you see. That would result in 2 to the power of 10 connections, right, between your input and the neurons. And then you have to connect all these back with the final neuron, which is you're going to use probably for classification or something. So you need this many parameters to define just this one hidden layer to connect with your inputs. And if we go breadth-wise, that means we increase the number of hidden layers. We still have the same amount of input. We have the same amount of neurons. But instead of putting all in just one hidden layer, we put 5 maybe on 2 different layers. And now, if we connect everything together, you realize that actually each layer is just to the power of 5 parameters. And, okay, this is 5 to the power of 5. And but when doing this, it actually allows you to compute all these parameters and store them more efficiently and compute them more efficiently. So that's why people like to use layer sizes, but really much deeper.
Wait,
together.
Yichin,
Yeah,
why is it 2 to the power of 10?
to the power of 10, because you have 2 inputs, and each input is connected to every single one of your neurons.
10 square?
Is it? Did I do my math wrong?
Wait, isn't it like just 2 times 10?
Wait,
Yeah,
wait, wait, wait.
isn't like, you mean how many weights is it? Like,
Yeah, how many weights? How many weights?
then it's 2 times 10, right? 1 is connected to 10, 2 is connected.
Yeah, 2
which
times,
means
2 times 10,
Oh,
yeah.
it's 2 times 10? Did I do my math wrong? You sure about that? Combinations. 2 times 2 plus 2 times 2. Isn't 10 times 2 times 2? Wait, what? Wait, am I getting confused, or is it actually 2 times 10?
Because like from x1 you draw 10 lines. From x2 you draw another 10
yeah,
lines.
that's true. Okay, but anyways, yeah, my math is wrong then. So, but anyways, doing this way is more computationally efficient. Actually, empirically prove it. You can go try yourself, right? And the another reason why you want to do this, which is a bit more hand wavy, is that this depth-wise structure actually allow you to learn hierarchical features. This actually sort of harken back to the original taster course that we gave. We would talk about a CNN, right? So we talk about how the CNN takes it's essentially building up on features, where your initial layers might be analyzing stuff like edges. So your front layers, if you stack all these up, your front layers is actually extracting edges, which are lower level features. And then the second layer, the second hidden layer, is building up on these extracted features to create stuff that's more complex, maybe stuff like objects, right? And eventually, if you have another layer, you can take these previously extracted features to make something that's even more complicated, like faces. And then it goes to people and stuff like that, and so on. Right. So by having all these layers stacked together, you're allowing this hierarchical construction of features, which people have found very useful, and it sort of serves as the foundation for many different architectures, especially CNN. Right. So these are 2 strong reasons why you want to do that. So that's for universal approximation. Let's talk about next how we can visualize, just for a bit, visualize our a simple neural network. So let's have input x1 and x2. Let's have two neurons in the hidden layer. So they are densely connected. Right, every single one is connected to every single one. And then you have, so in this layer is W1, 1. This is W1, 2. W2, 2. And this is W2. Oh, that's W2, 1. W2, 2. Right, so all these different weights. And you have bias in each one of these. And then let's just put each of these neurons through the activation. So let's just say this is F1, this is F2. So from the output of this, you go to F1, this one goes to F2. And then finally, we'll be summing it up. But let's, in this case, just consider this two outputs here. Because the last one is just your linear classification based on these two features that you have extracted. So let's say we have a data set that looks something like this. X1, X2. We use different colors for different data set at different points. So let's say we have pink color here, and then some pink here. And then we have different clouds here. This is not linearly separable. There's no line you can draw that will perfectly separate your data set. If we are to visualize, essentially, with this network here, neurons can be represented as a sort of decision boundary. Say in this case, let's call this 1s, 2. Our decision boundary in this case, training network could look something like this. So this one, say, face inward, facing inward as well. And because each of these are put through a activation function, the decision boundary is actually not clear cut, right? It's not transitions from positive to negative. Instead, it process if you put your sigmoid advantage, right? So it's essentially for this decision boundary of a positive value, and slowly transitions into a negative value. This is going to be a negative value, and then transition into a positive value. Right, so it's like a smooth gradient sort of thing. And then so if you visualize this in 3D, this is essentially like a hump, right? Essentially like a hump. Okay, and if we plot our F1, F2, you can observe something quite interesting. So if you take this point, for example, for, let's say this is our F2 and this is our F1 decision boundary. This is our first decision boundary, this is our second decision boundary. So you can see that on the second decision boundary, this point here will produce a negative value, right? Quite a negative value. Whereas with regards to the first decision boundary here, this will adopt a positive value. So what happens is that this one will, let's see, where will it go? Oh, actually, it will, let's see, let's draw somewhere here. So this is F2. So your F2 will be negative. So it will be somewhere down here, whereas your F1 will be negative. Or it will be positive, pretty positive. So maybe somewhere here. Somewhere down here. And then if you take a look at this point here, for the F1, after you put through the activation function, this will be negative, right? Whereas if you're taking a look at the F2, it's very positive, right? So what will happen is that it will be somewhere possibly here. and if you take a point that's in the blue region, you'll realize that both the activation functions will give you a positive value. So perhaps it will be somewhere that's here. And if you do this for, you repeat this entire process and try to plot it on this graph for every single value in the data set, you realize that for this specific activation function, spreading out the points somewhat like this, and your blue points will all be accumulated here, which you'll realize that it's linearly separable, right? So if you take F1 and F2 and use them as input into this one single neuron, you're essentially putting a linearly separable set of features to allow this neuron to properly classify it. So that's one way you can visualize what a neural network is doing. And by essentially increasing all these hidden layers, you're just increasing the likelihood for one representation to be linearly separable such that the final neuron can actually use it to classify correctly. With that, let's talk about finally how to train this neural network, because we have talked about how we can use backpropagation for a really simple single neuron, and you guys already implement that. But in this case, we're actually dealing with many neurons chained upon each other's. So that's sort of a different thing, right? So backpropagation. The backpropagation algorithm is pretty much the same. We still require a label y, that's your ground truth, and let's say your output, predicted output is y hat. So you still need some form of loss measurement. So you need a loss function which takes in y and y hat. Right? Let's not define the loss function yet. So just say this is a general random loss function that you can use. And to update your weights, right? Because you have now many different weights in each of the layers. We'll denote each of a weight as wij, where I is the layer that this weight is in, and j is the jth weight in that layer, right? So to update that, you're essentially assigning this value. It's the same as your classic backpropagation algorithm. The loss dwij, right? So this is just your classic backpropagation algorithm. Maybe you want to write y hat. Yeah. So nothing has changed, but you realize that this quantity here is actually not too straightforward to calculate. So let's talk about how we can try to calculate this loss here using chain rule, right? Let's take a look at an example where you have an arbitrarily long chain of neurons. So let's say I go from the input x, goes into some neuron, and then goes into another neuron, and so on and so forth. This goes into the final neuron and produces the output y hat. So this has the weight 1, and this is weight 2. And we'll denote the output of x w1 plus w0. Let's just take all the bias as 0 in this case to be z. So in this case, the input to the first neuron will be z1, and then it will do some activation function with this input, right? So the activation function, and this will be z2, and then the activation function will be known as f2, and so on, until let's say we have L neurons, right, in this chain, and this will be the alpha weight zl, and then this will be alpha activation, which is basically the output. So let's just to clear things up a bit, z1 is equal to, because we set all the bias to 0, so w1 multiplied by x, and your activation function, let's in this case use 10h. So your f1 will be essentially the 10h of weight multiplied by the input, right? And your F2 will be equals to your second weight multiplied by the previous output, which is F1. And then you can keep doing this until you get to the last neuron, where FL is essentially equal to 10H of the previous. Let's do weight first. WL multiplied by the previous, which is FL minus 1, right? And let's say our loss, we need a loss function. Let's say our loss is the very simple one, just your squared distance. Okay, so this is a pretty simple loss function they can use. So our objective is to calculate essentially the derivative of this loss with respect to a arbitrary weight, because we want to update the weights, right? So let's say we want to start from the front. We want to update the first weight. So you to update the first weight, you need the derivative of the loss with respect to the weight itself, and you can express this as the F1, the W1, the loss over the F1, right? So this is equivalent, right? So we actually know how to calculate this. This is very straightforward. So this is essentially the derivative of the tangent activation function with respect to your W1. And actually the derivative of tangent is just equal to 1 minus the tangent squared. And then because you have to differentiate inside as well, so it will be x outside, right? So this is essentially equal to 1 minus f1 squared x. So we know this, but our main problem is with finding this. Right, so let's bring it down here. We can actually chain this together in relationship to f2. So d loss, we are interested in d loss df1, is actually equal to df2 df1, the derivative of the second function with respect to the first function, multiplied by d loss df2. So again, you can see that this is equivalent, and this again is a similar expression to this. So it's just 1 minus f2 squared multiplied by, in this case, the weight, which is w2, right? So you can just keep doing this until you eventually get back to the top. And let's see. So we can write the general one, the W1. We have to differentiate the loss with respect to the second the last activation, right? And then we multiply this by dfl dfl minus 1. This is essentially what we just did, but we are doing from the end instead, and so on and so forth. You keep doing this until you get to df2 df1, and then you can df1 dw1. And if you actually go ahead and compute this, your loss with respect to f2 is essentially a y hat, is just negative of y minus f2, right? And then this thing is just 1 minus f l squared multiplied by the weight, wl, and so on until you get to 1 minus f2 squared multiplied by the weight, and then you can do 1 minus f1 squared multiplied by x. And that will be your derivative of the loss function with respect to this weight. And you can stop at any point of this chain to find the derivative for any one of the weights that's involved in this entire computation. So this is a really powerful chaining method that is used to calculate your derivative with respect to any of the weights within the neural network. So this case is generalizable to when you have, say, multiple neurons in one layer. But the mathematics will be a little bit more involved, but it's still the same concept. So if you are interested, you can go try this out yourself. And but in actual practice, you do not actually have to worry about this, because we already talked about the usage of gradient tape that can help you to automatically do all of these. Or even better, you can use other libraries, right, like tf.kras, that will essentially implement all these dense layers for you out of the box already. So you just have to specify the number of neurons in each layer, and then you specify the activation function, and it will just do all these automatically for you. And we actually talk about how to use these powerful libraries perhaps in the next lesson. And actually, that's pretty much all I want to cover for feed-forward neural network. Yeah, it's actually pretty straightforward if you just ignore this bit. Yeah. Is there any question?
Wait, so to take derivative for a certain weight in, like, say, the Lth layer, you don't have to take the derivative of anything before it.
No, because it's not dependent on like the derivatives before it itself. Yeah. So if you have a neural network that looks something like this, and you're interested in one of the weights in this layer, you only have to care about whatever goes after that. Yeah. So all these things you can just ignore.
Wait, so like TF talking layer, is it just like a perceptron but combined,
What are you saying? I can't hear.
like the dense layer that you were talking about?
Yeah.
Yeah, is it just like perceptrons but like combined into a network?
So okay, what a dense layer is, right? Okay, maybe we should clarify this right now. So a dense layer is essentially a hidden layer. Let's say in this case, this is actually a dense layer with 1, 2, 3, 5 neurons. And a dense layer is where your input is, like each of your input is connected to every single one of your neurons, essentially. That is the dense layer. Yeah, so this is one dense layer. And then usually in your neural network, you'll be stacking a lot of these dense layers together. So the output of the dense layer goes to every other dense layer. Yeah, anyways, you know the connection, yeah. So yeah, this one row here is one dense layer. Yeah. If there are no questions, I will show you guys some simulations regarding weights. So let's see. How should I talk about this? Yeah, okay, let's do here. So from all the previous assignments, generally you guys have been initializing the weights to just be 0, right? So for your classifier, your theta is just equal to, like at first it's just like 0 or something like that. And your bias is also equal to 0. But in the case of a neural network, where it has actually many different neurons, you do not want to initialize your weight to 0. Instead, usually you want to pick from some random distribution, right? The important thing is that you should never initialize your weights to the same value, right? And based on the actually, there's perhaps two prominent explanation for why that's the case. So based on the calculation we did just now, right? If all your neurons are initialized to the same weights at the start, what's going to happen is that your gradients will all be the same. If you initialize everything to the same value, your gradient that's calculated will all be the same for every single neuron. And then as a result of that, the output to that, all the neurons will be the same. So essentially your model is just not doing anything. You're just having the same update to every single one of the neurons, and that's gonna render your network to be unable to learn. So you cannot initialize your weights to 0 or anything that's the same. Instead, you should pick from some random distribution. The second idea is that if we have, let's say, a really just some plot of the error surface, right? So you have some, let's say red means it's going like negative. So you have some perhaps global minima here that you want to go from your point, and then you have some like bumps along the way and so on. These are elevations, right? But you might have like along the way local minimas that's dotting the error landscape, right? So if you say drop off from a point like this, then it's very likely for your algorithm to go into a local minima and just get stuck there, right? So if you always initialize from the same with the same weights, you're starting the training from the same position, and you're going the same direction. So your model will essentially always go from here, and then it's go into this local minima. It's going to get stuck. But if you initialize your weights each time randomly, you're actually allowing your model to start from different locations of this error landscape. And perhaps there's a good location where it allows it to actually go to a minima that's actually lower than all these smaller local minimas, right? That's why you want to initialize your weights randomly. So I have this visualization here, which I can show you guys. Let me stop presenting and present again. Okay, let me show a normal neural network. Present again. Oh, you guys can see, right? So you can actually,
Yes.
yeah, you can actually access this page yourself later to play around this. So essentially, I have this data set here, and then I have some neurons, and these are all randomly initialized. Let's just do it again. Randomly initialized weights, so they're pretty close to zero, right, as you can see. So you wanted them to be close to zero, but they're never recommended to be the same. So you can go ahead and start training, and it's going to converge pretty quickly, and then it's going to find this pretty good decision boundary, right? So that's how the neural network is supposed to behave when you initialize all the weights properly. Now let's look at another one where you just initialize all your weights to zero. So this one. So in this case, you can see that all these weights are initialized to zero, right? And if I start training, it sort of just got stuck somewhere. And then if I go reset, there's some cases where your model won't even have any response at all. It's just gonna get stuck there forever, and all your weights get updated the same. It's gonna take a bit. You can search neural network calculator and you'll get this page. You can perhaps try it out yourself. Okay, if I just set everything to zero, and then you can see that the loss sort of just immediately died, and then it just stabilized here. And then it's not actually doing anything useful. And you'll see all the weights are being updated around the same values. So yeah, don't ever initialize your weights to the same values, because that just prevents its learning. And then finally, maybe just another simulation of a more complicated data set with a more complicated network. So we have this spiral here this time, and then I have 8 neurons here. And this is a pretty high learning rate. So it's spasming. I think you guys can tell why it's spasming, because the learning rate is pretty high. So that's pretty normal to have some randomness in your training curve. And you can try to play around with the number of hidden layers such that you get like a pretty decent approximation. And you'll notice that each time you run the algo, you'll actually get slightly different decision boundaries. Sometimes you'll get a pretty good one, sometimes you'll get a pretty bad one. So it's kind of up to chance, because usually your neural network gets stuck in some local minima, and that's kind of the best you can do. You can try different activation functions, maybe ReLU. This actually found a pretty decent decision boundary that's able to classify most of your things correctly. Yeah, so you can play around with the data set and different type of features. Actually, this one is doing better. Yeah, so this is called the neural network calculator. You can go play around with yourself. I will also be sending a link which has a little bit more discussion regarding the universal approximation theorem and how you can actually make use of these non-linearities to form those step functions that I was talking about to essentially approximate any function. And they'll also help you visualize it in a higher dimensional space. So if there are no other questions, I guess that's all.
Okay, I think I'm gonna say some stuff about Friday's lesson.
Yeah, sure.
So so basically it's been demonstrated just now that basically neural networks, they function based on heuristics, meaning that you are just trying to get a rough estimate of a solution, and because of the complex nature of many ML problems, the loss surface is very complex and you don't know where the global minima is. It might be impossible to solve the global minima, which is why people just try to find a local minima that is the best that they can find, and they just like are happy with that solution. That's what they call solving a problem by heuristics. And trying to gradient descent on such a complicated loss surface poses a bunch of challenges. And the two ways in which this challenge can be solved would be: one, choosing a more powerful loss function, and two, choosing an optimizer. An optimizer is something that allows you to update your weights in an intelligent manner so as to be able to go down the loss curve very quickly, and if everything is stagnating, find some way to escape a local minima to go to another local minima that is even lower on the loss value. So in the next lecture, we'll probably be going through information theory such as entropy, and this will be the basis of some loss functions that you will see very often in deep learning. They are of the cross entropy family. So you may be seeing things like cross entropy loss, binary cross entropy loss, categorical cross entropy loss. So I think we feel it's pretty valuable for you to know exactly what those loss functions are doing, why they were formulated that way, and also to understand things like optimizers, how they manage the intelligent updating of weights for you to solve your problem by heuristics. So that will probably be the topic of like the next lesson, and also how to use Keras, which is like the next library. Keras is basically like part of TensorFlow. Yeah.
Actually, another thing. Just a little bit. I remember. Wait, who came from round 2 actually? There's like 2 people that came from round 2.
Me.
Yeah. We gave
I
you
hate
guys
ResNet.
the paper about what?
ResNet.
ResNet. Yeah. Okay. So actually, from just now that derivation, let me just share my screen again. That derivation for the gradient, as you can see here, you can see one problem with this approach, right? Is that if your gradient at each turn, because it's depending on a lot of these gradients, right? If your gradient is really small, and you have a really large neural network, what will happen is that the final derivative will be close to 0, and essentially your network won't learn. And that's one of the reasons why your long chain of neural networks won't work, and you need the residual connections. So from here, you can already see like one problem with this approach, and then hopefully we'll go on to address this in later lessons. Yeah.
Like those that were in round 1, you may recall that the paper that we threw to you guys was VGG, and one of our interview questions was actually what would happen if you were to keep on increasing the depth of the model, right? Because one of the results of the research paper said that, if you have a deeper model, then you can get higher accuracy on the test set, right? Because the universal approximation theorem states that with higher depth, you have higher representational power. But this problem of vanishing gradient also happens, where the deeper your model, the more terms in your partial loss with respect to that specific weight, and therefore your gradients get pushed to 0 and your model learns very slowly. So there's a kind of a give and take, and you need to find a optimal balance. Yeah, again by trial and error. Wait, should we do the Hui Guan thing where everyone must ask one question?
I don't want to force people to ask questions, honestly.
Okay.
Should we give some random homework?
I don't
Please,
know.
no, please. Please.
I don't know, man.
Wait, can you like explain like what is the what is the time head function?
10H function?
Cause yeah, cause just now you only cover like the sigmoid one.
Oh no. Okay, so sigmoid is a class of function, right? That looks like an S shape.
Oh, okay.
So 10H is actually a part of a is a class of sigmoid function. In the but from the it differs from the classic sigmoid function in that the value range is different because the classic one is 0 to 1. In this case, the 10H goes from -1 to 1. Yeah.
Oh, okay. Within value is just like you cut off the negative values. Right?
Yeah, the negative values go to 0. Yeah.
Okay.
Actually, if you play around with that simulator, the neural network calculator, if you use ReLU, you realize that the decision boundaries for a smaller scale neural network would be pretty rough in comparison to the smoother sigmoid functions.
Oh, yeah. So ReLU, right, because it cuts out negative values, is more suited for computer vision applications because there's no such thing as negative pixels in an image. So that's why they just throw away all the negative information. But some people have also argued that cutting out this information entirely is not very good because it also leads to loss of information, loss of features. So there's actually this thing called leaky ReLU, where on the negative side, you can just multiply like a very small coefficient to the features. For example, 0.001. So it will allow some of the information to leak through, even if it's negative. Then, so yeah, ReLU is used for computer vision. Then, as for why TANH is used for things like NLP, is because earlier on you saw, right, the TANH is the S-shaped curve but centered about the origin. So that would mean that means that it's actually like easier to it's actually easier to do the back propagation because like your values are between -1 and 1 as opposed to more of your values are near the -1 to 1 range as opposed to sigmoid where more of your values where more of the values like in the we actually no, that's not a convincing reason. Okay, you know what? 10H, I can go and Google why 10H is more stable for backpropagation.
Actually, one of the reasons why sigmoid functions are more stable is that their gradients will never go to 0. But they can still get quite small if your values are too big, which is why you need regularization.
Okay. So for some people like sigmoid, cause yeah, the gradients never go to 0. But for 10H, there's also reasons online that state is always better than sigmoid because it outputs a positive and negative values. So for NLP applications, where for example you don't have a constraint of things like negative pixels don't make sense, you can have this retention of information by outputting from -1 to 1. And the other reason is because the derivatives are larger. If you look at the slope of the 10H curve, it's more obvious, meaning that it can help you escape local minima. Okay, and finally, earlier on I mentioned that 10H is centered about 0 and this makes backpropagation more stable. Okay, I found the reason. Apparently, if you consider an edge case where, let's say, all of the outputs that are fed to a certain hidden layer, they are positive, that means that when you do backpropagation, your changes, the change, like the difference between the outputs and the correct answer, will also have the same sign for all possible neurons. And this will mean that your changes that you want to update to the neurons will also all have the same sign. And this is undesirable. This will mean that every single kind of gradient descent step that you want to take will involve like the changes to the weights being either all in the same direction, which is positive, or negative. So you can kind of imagine the values of your weights either all shooting up or being depressed down at once. So the model is kind of zigzagging, and that's not good. So by having the function centered around 0, this allows the average of, let's say if you consider a hidden layer, it allows the average of all the outputs of the hidden layer to be closer to 0, and this prevents this zigzagging problem.
Okay, I think if you guys have no questions, you can leave. Oh yeah, should we get homework? Like implement
Use Keras.
no implement from scratch, something like that.
Oh my god.
You guys want to do it?
Yeah, we can't even use tensors. We should use lists.
Okay, then for Wingyet, please implement a deep neural network from scratch using lists.
Yes, sir.
By tomorrow. If you don't hand in tomorrow, you are no longer ML section. You go to CP or something.
We are holding a farewell session for Winnie now.
Wait, can I share like what do you do last year during the TIL thingy? Like what kind of model they ask to do?
So it's split into two sections, right? It has the ML part, and then after that you take whatever you did in the ML part to apply it in some robot. So the ML part was also split into two different things. One is NLP, the other one is computer vision. So for computer vision, it's a more complicated one. You're essentially going to it's an object detection problem, basically. Yeah, you detect the type of clothing items that a person in an image is wearing. And then for the NLP, it's given a sentence, you identify the clothing items that are mentioned in the sentence. And then after that, based on there were two different Kaggle competitions for each of these topic. Then after that, you just based on your score in those Kaggle competitions, you'll go into the next round where you implement these ML models that you've trained in previous round to into a robot, basically. To then you go to the DSA headquarters to they have an arena there where you actually perform some task using those models.
Wait, but like, how does a robot thing work? Like just copy the model in or something?
Also, basically, the how was it? The robot had some Bluetooth or Wi-Fi capabilities. I remember it's Wi-Fi, I think. That it connects to one of the workstations they provided over there, and basically you'll run your model on that computer, and then it will relay information to the robot, which based on the information is gonna do something. It will send commands to the robot, basically. Yeah.
So we don't really need much specialized robotics knowledge.
I mean, for last year's, no. So I'm wondering whether this year will be the same, but probably. Oh yeah, we had to use a drone last year as well to take an aerial photo of the arena, so you can so that the and then use some algorithm to plan some route, such that there's some obstacles that the robot needs to get around. Then we use some algorithm to do that.
But what you say is what happened last year, right? It's not.
Yeah, what happened last year? So it's not guaranteeing what happened this year, but it's still going to involve some robots. So
Last year they did provide lectures, but honestly, right, the pace of the lectures is so fast that if you don't have prior experience, is pretty much cannot understand one lah. So yeah, we will try to build up your competency before the end of term 2.
wait, did they talk about object detection last year? Because I didn't.
They
attend
did
one.
they did they went through no they went
Oh,
from
they talk about
simple
retina
neuron.
there or something.
No, they went from simple feed-forward neural network, which is what we did today, to convolutional neural network.
Then
They whizzed through convolutional neural network, and then they went and talked about their variant of single shot detector, but they didn't even like they
the
didn't even say
YOLO.
yeah no it wasn't even a YOLO variant. It was their own custom SSD variant.
Yeah, then of course nobody's gonna use that thing. So
No, like people actually used it. I mean, I used it
legit?
also. I also used it. Yeah.
Oh, legit. Okay.
Yeah. So there's just like the objectness, one part to detect objectness, one part to detect class, and Huber laws to detect localization.
Any other questions?
Well, that means like for TIL teams, expect the lectures, watch them, record all of them if you want. Yeah, just I guess watch them for the stretch, but don't expect to be able to instantly understand them the first time that they give them. Yeah.
Or you prefer to figure out things your way, because we also didn't watch the lecture last year. I don't even remember what they talk about.
But anyway, learning point from our experience doing ML competitions is when it comes to competitions, these kind of competitions where you have a robot application, that means that not only do you need to think about accuracy, you also need to think about throughput or the how big the model is, whether it can execute in real time or not. And you will want to whack state-of-the-art solutions, pre-train if possible, and fine-tune.
Oh yeah, basically don't build your own stuff. So if you can, just go find some REPL, and then you try to tune their parameters and stuff instead. Unless it's a really simple task like that NLP task that we were given last year, where you just have to detect the clothing item in a sentence. That is really simple. So we actually made our own model and stuff. But yeah, other than that, you should, for more complicated tasks like object detection, you should really use pre-trained stuff or available architectures online. Yeah. Also, if you get into finals, I think they will give you free ice cream. That's what you got last year.
Actually, last year the NLP segment, right? They actually went quite easy on people because normally, if you are given an NLP task, you're given the raw text. You need to tokenize yourself. You need to remove noise, useless characters, and you need to create your own embeddings. For them, they literally gave you the embeddings and they gave you the word indices straight away. So everyone was getting like 98% accuracy, and for those at the very top, it was basically like a competition between, I don't know, 10 to the power minus 3%. So yeah.
Actually, their scoring system is really fucking bad. I'm not gonna lie. Like, it's really bad. They don't normalize it. It's just literally by raw placing.
Yeah, this year they might change the NLP structure to
You
make
just
it
trigger
harder.
a flag. Now it's gonna be harder for sure.
I don't know, man.
You just triggered a flag. Okay, guys, if the NLP task is too hard, you guys can just blame Alistair.
Bro.
Okay, no question, just leave. Okay, I wanna go, guys.
Well, I'm going to say before you leave here, so we can log out your timeout.
I wanna go eat it, man. Come on.
Bye. Thank you.